On slide 6, I show the analysis steps, which I describe in table 1 of the paper. There are 5 steps. Step 1 is trying to find if there are cycles and what they look like and what their duration is. So this is sort of an exploratory step for which cross-classified DSEM is especially useful because it allows for estimation of between time estimates. So time-specific estimates that can describe the cycles. And you can plot then the observed means and these time-specific estimates to take a look at what the cycles, what shape the cycles have. So this is an exploratory step, whereas step 2 then takes the confirmatory step where you fit cycles to a specific cosinor model. That is a model with a specific shape for the cycles. So it's very much like the exploratory confirmatory steps of factor analysis. And we're going to start step 2 with using fixed cycles coefficients. I'm not a fan of starting off with random effects right away, but I'll try to learn first about the model using fixed coefficients. So that's what I'll show you. And we're going to take a look at cross-classified DSEM again, like in step 1, but now with certain cycles imposed based on the step 1 features that we saw in the plots. And I'm going to show how to plot these estimated curves using the loop plot features of Mplus plotting. Step 2 can also be done for bivariate 2-level RDSEM, which I'm not going to talk about right away, but towards the end in the epilogue when we come back to the relationship between PA and tiredness. So we get that bivariate model once again that we looked at on slide 5. In step 3, we have an interesting step where you try to find deviations from cycles. We'll never find a model that fits perfectly, and we want to be able to capture deviations, and the deviations themselves can be of substantive interest. Now, cross-classified DSEM is again very useful for testing which deviations are significant in a very simple fashion. I'm going to show you how to do that. And then you can add those add model components that capture those deviations, that account for them, and you plot that together with also time-specific dummy variables that can be added. In step 4, only in step 4 do we go to random cycles coefficients. And I can do that both in 2-level and cross-classified RDSEM in Mplus. And once you have random cycles coefficients, that is cycles coefficients that vary across individuals, so different individuals have different cycles, then you can take step 5 and try to explain that variation across individuals by individual specific covariates, time invariant covariates, background characteristics of the individuals that can explain why certain individuals have, say, higher amplitude in their cycles. And in that connection, we're going to talk about the Mplus features of multiple imputation and translating to what I just mentioned, amplitude and phase of the cycles. On slide 7, I will show the modeling in terms of a figure, and throughout this talk I'm going to talk modeling in terms of figures and not formulas. For those of you who want the formulas, you have them in the paper. Now we're going to focus on the bottom part of the picture, ignoring this top part here. And you have one variable here, y, and if you go back to slide 5, you see then that that corresponds to the top part of the picture, one outcome, and with a within part and a between part, not all of this other complexity. And that's how I want to start. I want to start univariate with a univariate model. And this part down here is what I call a DSEM model, whereas when I add this top part here, it becomes cross-classified DSEM. So the DSEM part is what I discussed in Webtalk 6. So what you have here, you have two time points, t and t minus 1, and you decompose the observed variable into a between part, variation across individuals, between ID, and within individuals, that is, across time. And you see that these arrows go to the y box without any residuals. The residual is 0. That is, we just write y as yb plus yw. Simple algebraic relationship. Just decompose it. So then we can talk about within individual variation, where this within variable is regressed on itself at the previous time point. This is a lag 1 model. We could have a lag 2 model if we want to, with an auto-regressive coefficient rho here, and a residual in that relationship. In addition to that, y is influenced by this between level variation, which we call a random intercept. So this is the random intercept description of DSEM. And again, this is covered in Webtalk 6. And the interesting thing then is that when you write it this way, you have a direct translation to Mplus input, where the Mplus input, the model statement, the model command, has a within part and a between part. So in the within part, you have this regression that you specify, and the between part in this case just has a mean and variance here. But it could have a quite complex model here as well on the between. Now we're focusing in this web talk a lot on cross-classified DSEM. So it's a cross-classified model, and that is an expansion of regular DSEM to add this part, where for each time point we add a latent variable, a further decomposition, a time-specific component, capturing time-specific variation. So you have y for the between time component. The cap t stands for between time, and this is time point t. So this is like a factor, or latent variable, continuous latent variable at each time point. And these can be estimated, and these can be plotted. So this can capture, in an exploratory fashion, can capture cycles variation across time. And that's the nice feature of cross-classified DSEM. So on slide 8, we show the results of the analysis in terms of a plot. I'll show you exactly how the analysis is set up later on. But here is the result of it. We get a time series plot for these between time estimates that we achieve by doing cross-classified modeling. They are in blue, and we see them for the 7 weekdays here. So we see the cyclic behavior of the blue curve. No cycles function imposed, but we certainly see this feature of going up and then going down. So these are called, these blue values are called B2A in Mplus internal notation, between level 2A. Cross-classified has two between levels, between ID and between time. Between time is 2A. Minor detail. In any case, you see the red curve then, which is the means over subjects, follow this blue curve, or rather the blue curve follows the red, since the red is the data. But you have more fluctuation in the red curve. like here for instance, but we should remember then, as the paper points out, that many of these points are based on very few observations, very few people, and may only be due to one person, for instance. So we reduce the variation in the data by modeling it by the cross-classified model, but without imposing a specific cycles function. So no cycles function is imposed here. It's totally exploratory. We just have a multi-level model which stabilizes the graph, and it's an easier way to look at the data. It's a more succinct way to understand what the data is like. Now we already see some deviations here. Friday and Saturday, it seems like the observed means are a little higher than what's predicted by the cross-classified model. And those are the kinds of deviations that we're going to focus on as we go forward. On slide number 9, we see the step 1A input for cross-classified DSEM. We see the 3 parts: between person, between ID variation, within person variation, and a between time variation. So let's see how that plays out in terms of input specification. Use variable list is equal to PA. So PA is what Y represents here in the general notation. It's a univariate analysis, single variable across time. And now we have a cluster variable setting with 2 variables on the right hand side: ID, that is person, and time. Then we turn to the t-interval specification. It uses a variable called hours, which is an original variable in the data set that is on the names equal list. And we're going to handle it in terms of 3-hour bins, 3-hour intervals, so that the 24 hours of the day is represented by 8 time points. The time variable that is such created is called time, and it ranges, it's an integer variable that goes from 1, 2, and up. And that's the variable then that you can name yourself, and it should be the same as the second cluster variable on the cluster option. And we work with the lag model, lag1 model, and that represents then what we have here, a lag1 YW on YW t minus 1. We could have lag2, lag3 models as well, but we have a simple case here. The analysis then is type equals cross-classified, and the estimator is a base. We can only do this using base estimation. B iteration stands for Bayesian iterations, and the value in parentheses says that we should do at least 2,000 iterations to make sure that we have a dependable solution. Number of processors is 2. Even if you specify, say, 8, you will only use 2 here in the computations. The model then corresponds to the 3 parts here, the different colors: the within, between ID, and between time. And ID is then the variable that you have here in the cluster option, and between time, that time variable is the same as this. So time should be the same in between these 2 and also over here. So on the within level then, we regress PA onto itself at the previous time point. This means that &1 means lag 1. So that corresponds to the specification over here. So that's that linear regression with a autoregressive coefficient that I call rho here. On the between ID level, we estimate the variance for this YB variable, and we also actually estimate its mean by default. On the between time level, we also estimate that variance. That's the variance of this variable up here. And that variance is then called PA, and on that level the mean of that is 0. So mean of these are always 0. And note also that one cannot have relationships between the y circles up here in the between time box part of the model. Now what we're going to focus on is plots here to learn about what the potential cycles may look like, their duration and shape. So we ask for factors, all factors, and 200 draws. So just a note here that by factors we really refer to any latent variable, not only a factor analysis factor like obtained by f by something, but also a latent variable like the yb here or the yt here. And if we wanted to have a random autoregressive coefficient here, then that random coefficient, that is a coefficient that varies across individuals, would be yet another latent variable or yet another factor. So if you focus on this variable here, the between time variable, which we want to estimate the values of and plot, what we do in the Bayesian analysis is, after the analysis has converged, this statement here asks the program to make 200 imputations. That is, you re-estimate the estimates and this value 200 times. So this value, this latent variable, gets 200 values. And then we take a look at the mean of that distribution of 200 values, or the median if we want to. So that's the posterior distribution. So just as a Bayesian aside, a latent variable like this is just like any unknown quantity in the model. That is, like any parameter. So it gets estimated, and we have a posterior distribution for it, just like we have a posterior distribution for a parameter. And we then choose a point in that posterior distribution. So these 200 draws then captures the uncertainty in that estimate. We're used to factor scores where we have only one value for a person, but you can also have several values, so you take into account the uncertainty, not only the standard error, but the whole distribution. Now, often it is sufficient to have maybe only 50 draws here. And actually, we have a paper on imputations that discuss how many draws you may need for different situations. So this is the setting. This is the input for the first step of analysis.